Hey everyone, thank you for tuning in. Just adjusting my audio. Okay, I think we're good here. Thank you so much for joining today. When I first started this channel, I had a lot of technical difficulties and I was trying out different streaming solutions, and I reacted to this one video that was really amazing. I think this is one of the best videos for explaining how and why AI works. And this will help you build an intuition and think about this in a new way. And unfortunately, the technical difficulties that I experienced made the video basically unsalvageable. I mean, it was okay, but I don't really recommend going back and watching it. So instead, what I'm going to do today is I'm going to revisit this conversation, and in hopes that I can do a much better job of covering it now that I am getting the hang of doing these types of streams. And so if you're new here, I do daily streams, usually an hour plus streams on intellectually stimulating topics. So you can just come and listen. And I usually talk about technology and the way that it impacts society. And you can just come listen anytime, drop by. There's an endless amount of content here. So if you like that, click like, subscribe, leave a comment. I love getting comments. A lot of people, they disagree with me on some things. They leave a comment and we debate. And sometimes I even have them on my show and we discuss. And so I'm a tech entrepreneur and engineer. I started a venture-backed company, and I am very interested in AI. So let's dive in. Okay, I'm gonna pull up this content here. So this is my channel. And if you scroll down on my channel, you'll see this playlist called Sources. And this has all the sources of the major videos that I've done reactions to thus far. And so this one is the one that I had previously reacted to, Why Neural Networks Need Layers by Art of the Problem. It's very good. And so I'm going to react to it again. Let me enable audio really quickly to make sure you can hear this video. And I'm going to put it full screen, and I will put on closed captions. Okay. And this is part of a series, but you don't need to have watched the other videos in the series. This video stands on its own.
So far in this series, we've looked at how deep learning was a paradigm shift in AI, where intelligence is understood to be the ability to learn instead of following human instructions. The problem is, most people see neural networks as some kind of magic. It's not clear why they work. And so in this video, we'll explore the guts of a neural network. Recall that a neural network receives an input, which we could call a perception. This could represent an image, sound, text, anything we want a network.
Speaking of technical difficulties, okay, now it's showing up. Okay, it has to do with switching tabs. I'm going to start over. Let's go.
In AI, where intelligence is understood to be the ability to learn instead of following human instructions. The problem is, most people see neural networks as some kind of magic. It's not clear why they work. And so in this video, we'll explore the guts of a neural network. Recall that a neural network receives an input, which we could call a perception. This could represent an image, sound, text, anything we want a network to perceive. A perception boils down to a list of measurements that are provided as input as a list or vector of values. For example, if it was an image, each value would represent a single pixel's value in that image. And these values are represented as electrical pulses, which are sent to the first layer of neurons, which we call the input layer. And based on these values, some of the neurons in this layer will fire in a predictable manner and send off a pulse to the next layer of neurons, and this process repeats, creating a wave of electrical activity that passes through all the layers in the network. At the final output layer, certain neurons turn on or off. The output can describe the degree of belief that the input is or isn't some concept it's been trained to recognize, based on the activation level of the output neurons.
Okay, so that was kind of a lot coming at you really fast. So I want to walk you through what he said so far. So essentially, a neural network takes data as an input and it has some output. And so this output is often thought of as something called classification. So let's say that you go back here. I'm going to go back and show you this picture that was earlier on in the video. Oh, I guess it's coming.
Of a neural an input, which we want a network to perceive.
So
A perception boils down to a list of views. Measurements
there was a
that
picture of a dog here somewhere. I will find this picture. But the point is that I don't know why the image is not coming up. But the point is that there was an image of a dog. So when you have an image of a dog on your computer, that image is encoded in binary. So there's a bunch of bytes of data, and that data is basically just a big long string of numbers. That's how images are represented on your computer. So when you take an image and you put it as an input into a neural network, the numbers that represent that image go along this starting point of the neural network on the side here. And so the way that he was explaining it is that each pixel on your screen represents a single color. And essentially what an image does is an image defines what value is at each pixel. And so if you have an image of a dog, you're going to have a file that's going to have a big, long list of colors, and that will be encoded as a series of numbers. And that is the type of thing that you can put into a neural network. Now, on the other side, there are things that you are classifying these images into. So let's say we had a basic AI that will distinguish between a dog or a cat. So if you put a picture of a dog, it says dog. If you put a picture of a cat, it says cat. When you do that, what you're doing is you're taking an arbitrary file. I mean, these files could have any sort of patterns in them. You don't know in advance what set of colors are going to be used to paint this dog or this cat. There could be a brown dog in the corner of the image. There could be a very large cat it's just all zoomed in on the cat. Like you can see there's a very wide variation in the appearance of dog and cat images. And there's no very easy way to determine if an image is of a dog or is of a cat. What you have to do is you have to find patterns within the image, and you have to use those patterns to distinguish between the dog or the cat. But the problem is that breaking that down and actually coding that by hand is almost impossible. I did an episode on Software 2.0. You should look on my channel for references to Software 2.0 and Andre Karpathy. I've covered this a lot in the context of this thing called Software 2.0, which is basically, it talks about the limitations of what you can do by hand. There's some things that are too difficult to code by hand by writing the code manually, and instead you need to use neural networks and other types of optimization techniques in order to build this type of thing. So one of these types of things that is very hard to build by hand is an image classifier. And the input image could be anything. And then, but on the other hand, it's either a dog or a cat. So that is a very simple outcome. And what you're trying to do is map all the possible pictures that you could input into the neural network to an output state of either dog or cat. So he's going to break down how it does this. Essentially, what he's first saying is that the inputs here activate certain values in the next row. And we're going to get into this a bit more. And then this will then activate values here, and this will activate values here. And as we go along, the deep neural network is called a deep neural network because it goes for a long time. As we go along, it's going to eventually get to this endpoint where it's going to output a decision. Is it a dog or is it a cat? So that's how he's setting this up. But he's going to actually describe why this works. and a bit more about how it works as well. So let's continue listening.
And based on these values, some of the neurons in this layer will fire in a predictable manner and send off a pulse to the next layer of neurons, and this process repeats, creating a wave of electrical activity that passes through all the layers in the network. At the final output layer, certain neurons turn on or off. The output can describe the degree of belief that the input is or isn't some concept it's been trained to recognize, based on the activation level of the output neurons. A key question is, how does a neural network connect perceptions to concepts?
So just to be clear, the perception is the file with the image, with all the pixels. It's a bunch of data. It's a big string of numbers. And then the concepts are either dog or cat. So it's mapping a variety of different image configurations to one or two values. And of course, in the case of a real world problems, you're classifying more things than just dogs and cats. You are, like, for example, predicting the next token in a series of texts or something along those lines. But we'll get into that more. So let's continue listening.
Put another way, if we freeze a neural network as it's processing the picture of a dog, what is it doing inside right before it knows it's a dog? Let's start with the simplest.
This is a really interesting question because we didn't always have a good answer for this. Neural networks they're actually a pretty old concept, and they were inspired by studying how the brain works. And we didn't always know exactly how or why they work. And to some extent, they're mysterious. But what was true is we did know at some point that they did work. And what you would do is you would feed images in, and you would then get a result, and then you would basically do this thing called backpropagation, where you adjust all the settings on each of these neurons based off of how well it did. So each time you're basically improving it by a micro amount. We're not going to get into these types of details in this video. We're going to talk about things from probably an angle that you haven't heard of before. But it is very interesting that we knew that this worked for a long time. We knew that you could put in data, classify results, train it to be more accurate over time, and that it worked, but we didn't know exactly how or why. Like, why exactly do these perceptrons, the activation of these perceptrons, lead to a correct answer? It's not necessarily intuitive as to why that would work mathematically. And we're going to explore that a bit in this video.
Died right before it knows it's a dog. Let's start with the simplest possible neural network, a single neuron with just one input and one output. You can think of a neuron as a switch. The input is represented as a number, which is the value of something being measured, such as the temperature outside. If the input value is above a certain threshold, what we call the activation threshold, it flips the output on. Otherwise, the output remains off. And to better understand the guts of a neural network, we'll need a mathematical model of this simple switching action. Imagine the input value or temperature is a point on a line. The position of this point depends on the input value. We can think of this as our perception space. It's one-dimensional because we only have one input.
So let's just take this example at face value. So basically, you think of a neuron or a perceptron as something that just activates at a certain threshold. And so you can think of it as dividing just a scale into two. So for example, let's say that you weigh a certain amount, and at some point you would be considered obese. So if you hit that threshold, then people would say you're obese, and if you were below that threshold, people would say that you're not obese. You could use a neuron to model that, for example. And so in this case, we're talking about temperature. So let's say you wanted to classify something as being hot or cold, right? There would be some point at which you would start to say that things are very hot, or you would say that things are like borderline hot and cold, and like imagine that you just kind of moved this switch around. Like first it was up, it was like 1,000 degrees, and you say, okay, that's very hot. So you move it way down, and then you move it down too much, let's say, and then you move it to a negative 1,000 degrees, and you say anything over negative 1,000 degrees is too hot, and then that would also be wrong, right? And over time you would adjust it, and then at some point, if you're just adjusting this activation threshold, what you would do is eventually you would find some temperature where typically when you get feedback that it's hot, it would be above that amount, and when you get feedback that it's cold, it would be below that amount. And that's basically like a one neuron example of how training a neural network works. But it's a very simple example because it's just a one-dimensional attribute. It's just temperature. But in the real world, real problems have many dimensions. And this is why it gets very hard to code these things by hand, and why we need neural networks is because we need some way to adjust parameters for a multi-dimensional problem. And as you'll see, adjusting parameters for a multi-dimensional problem gets very hard, especially as we get so many dimensions. And we're gonna show you an example of that coming up soon.
A neuron can be viewed as dividing the perception space into active or inactive regions. If the value is above the neuron's activation threshold, it fires down the output. And so when we train a neuron, we are moving this dividing line around by changing the weight of the incoming connection, which determines how much current is needed to trigger the neuron. Similar to a thermostat, where the input is the temperature and the activation point is where we'd like the air conditioning to turn on. So let's consider a neuron with two inputs. Perhaps the input is a temperature and pressure reading of the environment. Now our model will have two variables which can each define a position along a dimension. And so together they can be thought of as a two-dimensional perception space or plane, where every input to the neuron is a point in this 2D space. In this case, the neuron can be represented as a straight line which partitions the space into active and non-active regions. Any input on this side will trigger the neuron, and any input on this side will not. And this pattern continues if we add more inputs. We just move up a dimension. Each measurement or input can be represented as a point in three-dimensional perception space. And the neuron can be represented as a plane which partitions this space into active and non-active regions. Perhaps we want the neuron to act as a storm detector, for example. And so no matter how many inputs it has, a neuron is like a partition or linear separation of a set of data points in perception space. In higher dimensions, we just call it a hyperplane.
So we like to, when we draw things out and we think about simple problems, we like to think about 1, 2, and maybe 3 dimensions. And our space that we are in right now, you can go this way, that way, up, down, forward, back. That's 3-dimensional space. Now it gets tricky when you start visualizing things above 3 dimensions. And typically, typically, so you'll have like a circle would be a 2-dimensional shape. You'd have a sphere, which would be a 3-dimensional shape, and then you would have a hypersphere, which would be a shape. It would be basically a circle that's above 4 dimensions or above. And so we kind of just, at the point where you go above 3 dimensions, we kind of give up on visualizing it because it's basically not possible. And you just kind of have to think of this abstractly. And so now what I want you to do is I want you to think about a problem. Any sort of problem, like driving or anything that can be solved by AI. Like, what does ChatGPT solve? Like, it basically answers questions. And I want you to think about how many dimensions there are to that problem. Because it's not necessarily, like, you could say, okay, well, self-driving is, a car is driving in 3 dimensions, right? It's going it's going through space. But that's not really the right way of thinking about it. There are a lot of considerations that the car must have in order to, there's a lot of considerations that the car must have in order to know how to drive. And in that sense, there are a lot of dimensions to this problem. And basically the input coming into the car is this video feed, which has a lot of data. And there are lots of different patterns and things that need to be recognized in order for the car to know what actions it must take. And what you have to realize is that this is actually something that you could think of as like a very high dimensional space. It's not just like 2D or 3D. It's a very high dimensional space. And you can kind of, like, if you go back to this example, you can kind of think about how there could be all these different dimensions like humidity, temperature, and pressure. And all of those could, like, you could plot all of those. And sometimes you would find like high pressure, high humidity, and high temperature, and you might predict if that's a storm, for example. You would find patterns if you were to chart like every day, and you were to chart humidity, temperature, and pressure. You would find patterns where, let's say, all the storms happen to have a very high pressure and stuff like that. And storms usually have higher temperature, and you would find clusters of these dots in this type of 3D space. And what a neuron would do is a neuron would partition that space. And basically with one neuron, you would be able to kind of, cut off that space in some way such that one section of the space you could classify as a storm, and the other space could be classified as not a storm. Now, it may not be perfect. You'd have to basically slice through that space. Just like if you see here, this is a plane, a two-dimensional plane. It's like that's the same thing as like a one-dimensional line slices through a two-dimensional space. A two-dimensional plane slices through a three-dimensional space. Now you can imagine that you basically have this a hyperplane that will slice through a multi-dimensional space. And basically it will determine a threshold upon which it will classify something in a certain way. And now it may not, sometimes there could be a low pressure storm, and that might be a rare occurrence, but it's possible. And so it may not perfectly classify, it may not perfectly cut through the space and always make a correct prediction. But as we'll see, as you add more neurons, you're actually able to slice up this hyperspace more finely. So let's continue listening to this brilliant explanation.
Non-active regions. Perhaps we want the neuron to act as a storm detector, for example. And so no matter how many inputs it has, a neuron is like a partition or linear separation of a set of data points in perception space. In higher dimensions, we just call it a hyperplane. This is how perceptions, which are values measuring the environment, can turn into concepts, where a concept is a region in perception space. That's how the neuron knows how to feel a storm if a measurement.
So a concept would be a storm. An input would be pressure. Pressure is one factor that would allow you to predict that something is a storm, to classify the situation as a storm.
Is in the right region. But of course, reality is not always so simple because we can't always draw a straight line through our problems. For example, imagine a situation where we have two kinds of input measurements, temperature and humidity. And our input measurements arrange themselves in a perception space like this. The circles represent measurements of winter days and the X's represent summer days. Well, we can't draw a single line to separate these points. But if we have two lines, we can, separating the data into four distinct regions.
So in other words, with a single neuron, you could bake a decent like summer, winter classifier for this. So let's say that the neuron activated from temperature and humidity at this point. Like, look at this top line here. This would be pretty accurate because basically the circles would be winter and the X's would be summer. So as you can see, like as long as it was above this line, most of the summer days would be classified correctly. Only a few of them would be classified as winter, and none of the winter days would be classified as summer. So this is actually pretty good, but it's not perfect because there's no line that you could draw really that would get all of this. Like even if you kind of, I don't know if you can see my cursor here, but even if you kind of drew a line from here diagonally to capture this X here, you'd still have these circles that were like there's almost nothing you can really do to get all of them. Just you can't segment this space by just drawing one line. But as you see, with two lines, you can get 100% accuracy.
Each region is defined by the state of the neurons being on or off. If neuron 1 is on and neuron 2 is off, we know it's in this blue region. And that is why we need to use multiple neurons, so we have the ability to carve up the perception space into many more regions. And this is what the learning process does. By changing the weights of the connections, we move these partitions around to carve out regions around conceptually similar input points. So let's pause and summarize. A perception is a list of measurements that are inputted into a network. These vectors can represent a coordinate or point in perception space. The number of dimensions in this space is equal to the number of different input values. And neurons act as partitions in this space. And a group of neurons together define a specific region in this space. And these regions can carve out inputs which are part of the same concept. But so far we've been looking at simple toy problems, and when we move to the real world, things get a little bit more interesting. For example, the first big commercial application of neural networks was vision, specifically making a machine which can understand human handwriting, so that at the post office they can read human letter addresses automatically. This is a hard problem because everyone writes numbers slightly differently, so the machine must find the general pattern of each number. In this example, the input to our network is an image containing 784 individual pixels, and so we have 784 input dimensions, each which measure the brightness of one pixel. Using our spatial view, we can think of the image of each written digit we input to the network as a point in perception space. And if we take many real examples and plot them in the perception space, we get this. The points are not nicely clustered into regions, but scattered all over. And so to carve up this space into regions is going to be very difficult. The messy distribution of inputs in perception space is why shallow networks with only one middle layer struggle to divide categories up cleanly.
Okay, so let's think about this for a second. So you have all of these different digits that are handwritten. And as you can see here, this 9 is different from this 9. And this 9 is different from those. Now there are these kind of overarching patterns, and we can recognize what a 9 is. But this is not something where, like, a lot of the pixels will not necessarily overlap. It's not like you can just say if these pixels are highlighted, therefore it is it is a 9. It's not that simple. And it's actually, there's a lot of individual pixels, and each one of these is a single data point that is fed into this neural network. So let's go back to the way that this was conceptualized over here. Let's see. So what we have here is, here's the inputs. And the inputs are going to be defined by the value of each pixel in the image, roughly speaking. And now imagine that you were able to chart all of this. You were able to graph it out. And so you realize there's many inputs. So when you graph this out, it's not going to be a three-dimensional space. Like when we were going through this example here, I'm going back here, humidity, temperature, and pressure. This was a clean example to visualize because there was a three-dimensional space, and then we could basically segment the space with a two-dimensional plane. But every time you had a value for each of these metrics, you would plot it as a point in three-dimensional space. But now imagine that this is pixel 1 instead of humidity, temp is pixel 2, pressure is pixel 3, and so on. Everything is pixel 4, 5, and 6. We have to chart all of those. So if we go back here and we look at this, look at all these pixels, right? So this is the dimensionality of the space. And this is going to be very complicated. And so when we visualize we visualize basically the sets of values and their corresponding like both the input and the output values, meaning when we analyze the input data, meaning the image, and we map it to the output data, which is the classification or the concept. I'm going to see if I can just kind of zoom in here, or they zoom in for you. Okay, here we go. Like you see, this 3 is classified as 3. There's also a 3 over there and a 3 over there. These 3s are classified, but when you plot them out just based on the pixels that are being fed into the neural network, they are not all clustered in one place. So imagine drawing a line that segments the space for all of these 3s. That would be very difficult. There's not like a clean line or a clean plane that will do this. Now, there's a little trick here that makes this even more challenging than it appears. Now, you might think, well, you could, make a bunch of different planes and segment the space, and you could block off all of the different 3s. What you have to realize is that this is an oversimplification, because this is actually plotted in 3D space so that we could visualize it. So actually, you'd have to draw a much more complex multi-dimensional shape in order to truly segment off this space. So just like to be clear, I want to just reiterate what's going on here. You have an input image which has pixels. These pixels are very widely distributed in terms of the input space, meaning you will find numbers that have a lot of overlap in the value of what pixels are highlighted. Yet, even though there's a lot of overlap, they're going to be different numbers. Like you can imagine, like at some level, you can imagine if you write a 6 and you kind of don't go low enough to connect it, you're kind of close to writing a 0, right? And stuff like that. That's just like a naive way of thinking about it. But you can have basically images that in some ways are very similar, or look at how this 7 goes out a lot and then this 1 kind of goes out. So you can see how you can have inputs that are similar yet have a different answer. And if you lined up all of the different answers, like all the numbers 3, you're going to see that all the pixel arrangements for them are very different. They're not all super similar in terms of which specific pixels are highlighted. So let's continue hearing this explanation.
Pixel. Using our spatial view, we can think of the image of each written digit we input to the network as a point in perception space. And if we take many real examples and plot them in the perception space, we get this. The points are not nicely clustered into regions, but scattered all over. And so to carve up this space into regions is going to be very difficult. The messy distribution of inputs in perception space is why shallow networks with only one middle layer struggle to divide categories up cleanly. The way out of this problem, though, is to follow the way of nature. Organic brains use layers of neuron activations to process their inputs. The importance of depth, or many layers, is the least understood aspect of neural networks. So let's pause and consider a simple analogy to understand why multi-layered networks are better at partitioning the perception space than a single-layer network. Imagine this is our perception space and we have two kinds of input data types. Each neuron we add in the first layer acts like a fold in this space. With two neurons, we can make two folds like this. And we could keep going, folding and unfolding the paper to carve out regions to separate these points. This will take 6 separate folds. This allows us to then group regions containing the same type of points using a final neuron which activates if any of those regions are active. But now consider what happens if we layer our folds. That is, we don't unfold after each fold. So let's do the first fold again, then the second, then the third fold across that layer like this. That ends up carving the space in the exact same way, using 3 folds instead of 6. And if we were to continue this process with a fourth fold, it results in 16 regions. And 5 folds results in 32 regions. This recursive power of folding shows how we can get exponentially more partitions using the same number of neurons if we layer them. Practically, this means that neurons deep in a network are not simple linear partitions, but are instead activated by a complex pattern of linear partitions. And so let's look at how this works using a real-world example.
Essentially, he's drawing this analogy to partitioning the space to actually making a fold. And what you see is if you layer these folds, you're actually able to do an exponentially greater number of partitions. And so it gives you a lot more. It creates a lot more regions in the space with which you are with a minimal amount of compute. So if you have a very large space and a very difficult problem, by creating more layers in a deep neural network, you're able to actually get a very high resolution in terms of your ability to break that space apart and classify each region of that space. I thought this was a brilliant physical analogy to illustrate the principle using paper.
Using 3 folds and it results in 30 shows how we can get exponentially more partitions using the same number of neurons if we layer them. Practically, this means that neurons deep in a network are not simple linear partitions, but are instead activated by a complex pattern of linear partitions. And so let's look at how this works using a real-world example. Researchers took a neural network which was trained on real images, such as ImageNet, and then probed individual neurons to find out what activated them or what turned them on. If we probe neurons in the first layer of the network, we find they are detecting these patterns, which are looking for edges and points. Then they move to the next layer deeper into the network and probed those neurons to see what activates them. What they found was the next layers are activated by different kinds of textures. And deeper into the network, these textures get more specific. And as you move deeper into the network, the textures get more complex. And the deepest layers contain individual neurons that are activated by entire objects, such as dogs, wheels, houses, or trees. These complex activation patterns are possible due to the layered structure of the network. And so if we cut open a neural network, we'll find the deep layers contain representations of a perception based on what level of different things or patterns they contain.
So, this is a very cool research. You can go on distill.pub and you can look at this. And I've never really looked into how they actually generated these visualizations, but I love this. This really illustrates it well. So let's go back to this example of the self-driving car. And think about how you have an input video feed. So kind of like if you think about the various inputs into that, there's just like, there's almost like a lot of dimensions for this, like classifying an image of a number. You can think of how all these, the pixels of the video feed, in a sense, are like the inputs and the dimensions in space of for a self-driving car. So you have all these pixels. That's the input. And now imagine that you have a good number of neurons that are able to divide up that space, and they're able to detect things like edges, and they can see, like, they're not really getting any big ideas out of this, but they are able to highlight in certain ways when certain types of edges are detected, and if those edges are not detected, it doesn't tell you where to drive or anything like that. But it's if you see a bunch of pixels that are darker clustered together in a certain way, you could imagine how one layer of neurons could actually pick out such a pattern. Then you'll start, as you start taking all the different configurations of edges into account, and now those are the new inputs. And with different configurations of edges, you're now going to be able to see textures. So like if you look here at these images of these textures, you see there's lots of edges on these textures. And so if you are able to detect a variety of different edges, you can see how those edges combine to create this idea of textures. And these terms, edges, textures, patterns, this is their terminology, but you can see how the abstract, like the idea gets more and more concrete as you go along. And you can see how if you have a combination of textures, now you're seeing these different patterns. And when you have a bunch of patterns as an input, you're now able to divide that up and identify parts of something. So like, for example, you can identify signs. Once you identified like all the edge arrangements and the texture of a sign's surface and patterns within that, then you'll understand, you'll see like letters or a sign or stuff like that. And then at this final stage, you have whole objects like stop sign and like traffic light and things like that. And then, and maybe this isn't exactly what's going on for a self-driving car, I'm just trying to illustrate it. And then at that, once you have that context, that is the input for the classification of what the car should do. So it basically takes the incoming pixels, segments that space into a set of very abstract observations, and then it looks at those combinations and segments that space into increasingly more concrete things until you get to entire concepts and objects as we think of it. Or let's just call them objects, because then once you get these objects, like for example, you get a stop sign, a pedestrian, a road, a dead end, all these things, now you actually you have all the intellectual pieces needed to carve that space up into a set of concepts, and you can classify what action you should take next.
That are activated by entire objects, such as dogs, wheels, houses, or trees. These complex activation patterns are possible due to the layered structure of the network. And so if we cut open a neural network, we'll find the deep layers contain representations of a perception based on what level of different things or patterns they contain, which is defined by how active those specific neurons are. For example, an image of a dog would light up the dog-like patterns in the network. Finally, let's flip back to the spatial perspective to see this power of layers in action. Recall that our input, such as an image, can be represented by a point in perception space. And each of the following layer activations can be thought as moving that point to a new location. and it finally settles into a final space at the end of the network we could call concept space. And critically, the job of these transformations is to pull apart dissimilar points in concept space and push together similar ones. To see this in action, let's return to our real example, where we plot the points of various perceptions of different human-written digits. Notice at first, the points are scattered all over. But as these perceptions move through the network, gradually these points are separated into tighter and tighter clusters. And so each layer acts as a transformation that gradually disentangles these points. This allows the final layer of neurons to easily partition the data into separable regions, which represents the concepts, in this case numbers, we are looking to classify. And so the magic or true power of a neural network is entirely in this layered processing, because it allows the final layer of neurons to carve up concept space, where the points are nicely clustered, instead of perception space, which is hard or impossible to partition. That's how a neural network knows something is a number 3 or 6, based on the proximity to the 3 or 6 cluster. This partly describes why we have different mental feelings or intuitions when we see different objects. It's because different groups of neurons are being activated deep in our mind, depending on what cluster it belongs to.
So one interesting way to think about this is, so this is a really cool visualization. I think this is also a very important piece to fully understanding this. So you basically, there's two separate spaces, and both are legitimate and both are important. The input space is objectively very useful. Like, let's say you have video feed of a car driving. That stores real information that is quite useful about the situation, like what's going on the road. You might have pictures on your phone and of your dog. That's going to be that's a very useful thing. The reason you take a picture and encode that information and store it into a file in that way is because that's useful to you. It's a useful way of representing it such that it can be reconstructed. The pixels can be reconstructed deterministically on the screen, and it's something that people want to have. So that's all well and good. But the problem is that it's not something that could be easily understood, and easily analyzed. It's very messy because you're storing so many pixels. In a sense, you're losing what it is in the process. Like, it's there, it's encoded into it. You take a picture of a dog, you can detect that it is a dog, but doing so is very hard. What you're doing is you're kind of like trading off resolution for and like you're basically adding resolution, but then you're almost losing some information in the process. You're not really losing that information, but you're losing access to that information in certain contexts. So you have this picture of a dog, and this is great because you might want to see exactly what that dog looked like. And was the dog wearing a dog collar? You might want to ask yourself that. But when you record so much information, now you lose the capability of easily mapping that to the concept of a dog. Now, when you look at it, you're on the spot, you're reconstructing it and you're classifying it in your head. But if you were to have a computer go through your list of files and find the ones with dogs in them without any sort of machine learning, it's not going to be able to do that. It could at any moment display the image of the dog, but it's not able to actually extract from that image the concept of a dog. And so, in a sense, there's this input space, which is very useful because it allows you to reconstruct a high resolution input. And then there is this concept space, which is good for other reasons. Now, if you know that it's a dog, you don't know if it was wearing a collar. That wasn't that's not part of this particular classifier that we're talking about. It could be dog with collar, that's possible, but that's not the example we're going with. You're going to lose that information, but at least you know it's a dog, and there are reasons why that would be useful. Like if you wanted a picture, like you had millions of pictures and you wanted all the ones of dogs, and you don't have time to go through it, that's a useful thing to know. And so now let's like look at this again. Now here, I mean, this is of course a fake example, but this is in a sense like a two-dimensional space. There's dogs and cats, and essentially there's going to be two. You can divide this space in half, and you're going to have all the dogs on one side and all the cats on one side. You just need one line to separate the space. And on the other side, you have all of these pixels. This is a very high dimensional space. And so the concept space in this case is smaller than the input space, but both of them have their own uses, is what I'm trying to say. And of course, a dog-cat classifier is like a dumb thing to do. So this is a simplistic, contrived example. But the point is that these are two completely valid ways of thinking about the same thing. The input space, it has more information. Technically, it should, maybe with some loss of accuracy, encode the information that's in the concept space, but it's not basically it's not easily accessible when it's in this format. And so it's nice sometimes to have the concept space result. That is another valid and important way of thinking about the same data. So what a neural network is doing is, if you look at this, let's look at these transformations. It's, as you go through, it's kind of sorting them out, and it's sorting them into clusters. And when it does this, what it's doing is it's allowing the space to be segmented by more easily. And what it's doing is it's actually a transformation function going from the input space to the concept space. And at the end of the day, this is a very powerful concept, in part because all software can be represented as a function that transforms an input space to, and we could call it an output space. That's a way of conceptualizing software. And what it shows is that the fact that that's essentially what a neural network is doing is it shows that a neural network can approximate any function. So it shows that this is a super versatile technology.
Our neural network is entirely in this layered processing, because it allows the final layer of neurons to carve up concept space, where the points are nicely clustered, instead of perception space, which is hard or impossible to partition. That's how a neural network knows something is a number 3 or 6, based on the proximity to the 3 or 6 cluster. This partly describes why we have different mental feelings or intuitions when we see different objects. It's because different groups of neurons are being activated deep in our mind, depending on what cluster it belongs to. And these clusters can also be thought of as connected regions or manifolds. And so perceptions representing the written digit 6 would fall on one manifold, and the digit 3 would fall on another. And so manifolds are spatial regions which represent the patterns essential to a concept. These patterns are defined by the connection patterns or strength across the neuron layers. But so far we have only modeled how intuition works, that is, a rapid interpretation of some impulse, such as when you recognize someone's voice by a single syllable. This is what a single pass through a neural network simulates. The other big challenge is problems which require reasoning. Interactive problems, such as having a conversation or playing a game. These problems are sequential in nature and require things like a form of working memory. This leads us to the cutting edge of neural network research. How will a neural network learn to reason?
That was it. How do I go back? Having a weird technical issue. Here we go. So anyway, thank you so much for tuning in. This was just a short stream today. Just wanted to cover this video again.